On the first day of spring, Denver felt like the middle of June. That is not a metaphor, that is a temperature reading. And the models that were supposed to predict it missed. Right now, the worst March heat wave in US history is sweeping over the country, with temperatures so extreme that parts of Kansas are drier than the Sahara Desert. 5% humidity, 40-mile-per-hour winds, millions of acres of grassland across the Great Plains behaving like kindling. But the heat is only one layer of what is converging this week. As we covered yesterday, we saw a gigantic fireball explode over Ohio, and incoming CMEs from the sun all inside the same 48-hour window. Stay with me until the end, because tonight we are walking through the raw data from government sources that most people will never see, and the full picture is stranger than any single headline suggests. If this has you hooked, subscribe to the Skylab, because this story is still developing. The heat dome has not moved, the fire weather conditions are still critical, and we will be right here when the next piece of data lands. Comment below and tell us what you actually think. Is an atmosphere operating at the 99th percentile in March and solar activity arriving at the worst possible moment, a cluster of unrelated extremes? Or is the data quietly pointing at something larger? We genuinely want to know what you think. Now, let's get into it. Part 1. The models are already wrong. Something is wrong with the forecast, not wrong the way a weatherman gets it wrong on a Tuesday when he said 70 and it rained. Wrong in a deeper, more unsettling way. Wrong in the way that a thermometer reads correctly, but the number it shows should not exist yet. The National Weather Service, an agency not exactly known for dramatic language, has said that what is happening across the United States right now will, quote, almost certainly break records. And when government meteorologists use the phrase almost certainly, you should probably pay attention. Let's start with Denver, Colorado, on March 19th, 2026, the first full day of spring. Denver hit approximately 85 degrees Fahrenheit. Now, if you are from Denver, you might shrug. Warm days happen. But here is the part that should make you stop. 85 degrees in Denver is not a spring temperature. It is a summer temperature. Specifically, it matches the average high for June 19th in Denver. The city did not just have a warm March day, it had a June day, delivered 2.5 months early, on the astronomical first day of spring. It is as if the calendar and the atmosphere had a disagreement, and the calendar lost. Now here is where it gets interesting, because the temperature itself is not the most alarming part. The forecast called for roughly 83 degrees that day. The actual reading came in at 85. 2 degrees over might sound trivial, and in isolation, it is. You've gone over budget by $2. Not a crisis. But this pattern, this consistent 2 to 3 degree gap between what the models predicted and what the atmosphere actually delivered, has been repeating for multiple days in a row, and that changes the story entirely. Weather models are extraordinarily good at short-range forecasting. We're talking about some of the most sophisticated supercomputer simulations in human history. Within a 1 to 3 day window, modern forecast models are accurate to a degree that would have seemed like magic to meteorologists 50 years ago. They account for pressure systems, moisture content, wind shear, terrain effects, dozens of interacting variables, crunching billions of data points in real time. These are not rough guesses. These are precision instruments, so when reality consistently lands above the model's ceiling day after day, that is a signal. Not noise, a signal. There is a concept that some meteorologists are now using to describe this phenomenon, and it is called model drift. Not to be confused with climate drift, which is a different thing. Model drift in this context refers to the pattern where real-world atmospheric conditions systematically and consistently exceed the forecast outputs. The models say 83, the sky says 85. The models say 83 again tomorrow, the sky says 85 again, and again. Think of it like this. Imagine you have a scale that has been properly calibrated, tested, certified, and trusted for years. And then, over the course of a week, everything you weigh on it comes in 3% heavier than it should. You do not blame the objects. You start wondering about the scale. Here is why this matters at a deeper level. Weather models are built and calibrated using historical climate datasets. The mathematical parameters inside the models, the values that describe how air behaves, how heat moves, how ridges of high pressure develop and intensify, those parameters were derived from decades of observed atmospheric behavior. They are, in a very literal sense, a mathematical summary of the climate that existed when the data was collected. So if the atmosphere is now consistently behaving beyond those parameters, there is only one coherent interpretation. We may be operating in territory that the historical record does not fully describe anymore. The models are not broken, they're just anchored to a world that may no longer quite exist. And this is not just about Denver. Denver is the entry point, the vivid example, the number that sticks. But the phenomenon is continental in scale. Multiple recording stations across the American West and Great Plains have been logging temperatures above their forecast values over the same multi-day window. The mismatch is not a local anomaly. It is a pattern with geographic reach, and in atmospheric science, a pattern with geographic reach is never accidental. There is a term for what happens when you realize that your most trusted prediction tools are systematically underestimating the very thing they were built to measure. It is called a prediction failure event, and it is genuinely rare. We have the best forecast technology in human history right now in 2026, and the atmosphere is outdoing it, not once, not by chance, repeatedly, measurably, and across a region the size of several European nations combined. So the next question, the obvious question, the one that should be forming in the back of your mind right now is this. If the models are being outpaced by reality in mid-March, what exactly is the atmosphere doing that even the models did not expect? Because when you look at the actual upper-level data, the numbers stop looking like a heat wave. They start looking like something else entirely, and that something else has its own name. Part 2. A 99th percentile atmosphere. Picture a room full of 1,000 students who just took the same exam. Most of them cluster around the middle, the 70 percentile scores, the 60 percentile scores, the average. A handful score at the 95th percentile, maybe 5 of them hit the 98th, and then, at the very top of the distribution almost alone, is the student who scored in the 99th percentile. That student did not just do well, that student performed better than 999 out of every 1,000 people who took the same test. That level of performance is, statistically speaking, extraordinary. It happens, but rarely. You would remember it. Now apply that same concept to the atmosphere. The National Weather Service office in Houston, Texas, which monitors upper-level atmospheric data for a broad swath of the country, reported this week that mid-level atmospheric heights over the region have exceeded the 99th percentile. Let me translate that, because mid-level heights is one of those technical phrases that sounds abstract until you understand what it actually means physically. The atmosphere has layers. At roughly 18,000 feet above the surface, there is a pressure level that meteorologists call 500 millibars. The height of that pressure surface, how high above the ground you have to go before the air thins to 500 millibars of pressure, fluctuates based on how warm and how energetic the air column is below it. When it's hot and the atmosphere is inflated with energy, that height rises. When it rises unusually high, what you get is a phenomenon called a ridge. A strong ridge is, in simple terms, a heat trap. It is a dome of high pressure that suppresses cloud formation, blocks the intrusion of cooler air, and allows solar radiation to pump uninterrupted heat into the surface below. When that ridge height exceeds the 99th percentile, you're not dealing with a strong heat wave. You're dealing with something that statistically should occur no more than 1% of the time, less, possibly significantly less, when you factor in that we are in March and not the height of summer. This is not a bad heat wave. This is the kind of atmospheric state that meteorologists look at and reach for their superlatives, and the upper-level data does not stop there. There is a tool used by European meteorologists developed by the European Centre for Medium-Range Weather Forecasts, called the Extreme Forecast Index, or EFI. It is specifically designed to measure how anomalous a forecast event is relative to the climatological baseline, not just whether it is hot, but how far outside the statistical norm it falls. An EFI value between 0.7 and 0.95 is classified as extremely rare, the kind of event you flag, document and study. But there is another metric layered on top of the EFI called the shift of tails, and it measures how far the actual extreme values push past even the model's upper boundary. When the shift of tails approaches a value of 2, it means the event is not just extreme, it is exceeding the extreme edge of what the model considers possible. The models are saying, in their mathematical language, we have reached the boundary of what we have ever seen. We are there. Here is a useful way to think about what that means. Imagine a ruler that was made to measure everything in the known world. every heat wave ever recorded, every pressure system ever observed, every atmospheric ridge ever documented. Now imagine a heat event that is bending that ruler, not breaking it, not shattering it, but bending it slightly, consistently, at the extreme end. That is what the shift of tail's value of approximately 2 is telling us. The atmosphere is operating at the outer edge of the calibrated range. For historical context, extreme heat events in the record books, the ones we still talk about decades later, the European heatwave of 2003 that killed tens of thousands of people, the record-smashing Pacific Northwest heat dome of 2021 that pushed temperatures in places like Portland, Oregon, to 116 degrees, those events had EFI signatures in the extreme range. What is happening right now across the American West and Central Plains is operating in that same statistical tier. And the crucial difference, the thing that makes a meteorologist exhale slowly before they answer a question, is that those historical events happened in summer. This is March. This is the first week of astronomical spring. So here is the open loop, the question you should be sitting with right now. If this is 99th percentile atmospheric behavior happening in mid-March, before the sun has reached its maximum intensity, before the soil has fully dried out from any residual winter moisture, before the seasonal heat machine has even warmed up properly, what does July look like? Because summer is coming, and the atmosphere is already operating near its documented limits before summer has arrived. That question does not have a comfortable answer. But it has a geography, and the geography of this particular event is where the story gets genuinely surreal. Part 3. The geographic scale is the anomaly. Hold a map of the United States in your mind. Now imagine that map is not a political document or a travel guide, but a weather snapshot. A single frame frozen from the atmospheric movie that has been playing this week. In the southwest, temperatures are punching into the triple digits in March. Across the Great Plains, the air is so dry that it has ceased to function like air over inhabited land and has started to behave more like the atmosphere above a desert. Up in the Pacific Northwest, the story is different entirely. Flooding, rainfall, cold, and in Alaska, a blizzard, simultaneously. All of this at the same time. This is not a regional weather story. This is a continental weather event. When meteorologists talk about what is causing all of this simultaneously, they are talking about the jet stream. If you are not familiar with the jet stream, here is the simplest possible explanation. It is a river of air, a fast-moving band of wind that flows roughly west to east in the upper atmosphere, usually between 25,000 and 45,000 feet above the surface. That river of air acts like a fence. On one side of the fence, warmth. On the other side, cold. The jet stream does not just move weather, it organizes weather, it separates air masses. It is the reason that the United States has distinct seasons rather than a uniform climate from the Gulf of Mexico to the Canadian border. What is happening right now is that the jet stream has been forced into an extreme configuration. The technical term is a highly amplified pattern. In simple language, the jet stream has buckled. Instead of flowing in a relatively straight path across the continent, it is dipping sharply south in some places and surging dramatically north in others. Where it surges north, it pulls warm air with it. Where it dips south, it drags cold air down. The result is not just a heat wave in the southwest. It is a heat wave in the southwest occurring simultaneously with cold, flooding and snow elsewhere, creating a temperature gradient across the continental United States that stretches for more than 1,500 miles. Phoenix, Arizona was pushing toward 100 degrees this week. Parts of the southeastern United States were near freezing, 1,500 miles of separation, 100 degrees of temperature difference, or close to it. For context, you have to cross multiple climate zones on a globe to find that kind of thermal contrast in nature under normal conditions. We are seeing it across a single country in a single week. This matters for a reason that goes beyond the spectacle. Large-scale atmospheric patterns are more consequential than local weather anomalies. A single hot day in Phoenix is not a scientific event of note, but a pattern that simultaneously superheats the southwest, desiccates the Great Plains, floods the Pacific Northwest, and buries Alaska under snow, all driven by a single distorted jet stream configuration that is a story about the structure of the atmosphere itself. It is not the temperature on any single thermometer, it is the shape of the system, and the shape of this system is genuinely unusual. The specific mechanism that is sustaining all of this simultaneously is called a blocking pattern. A blocking pattern occurs when a high-pressure system becomes stationary, or nearly stationary, and refuses to move the way that the normal progression of atmospheric systems would suggest. Weather patterns usually move. High-pressure systems travel across the continent in roughly predictable tracks. When they stall, when they block, the same conditions get piled onto the same geography for days, not hours, days. And the longer a blocking pattern persists, the more extreme its downstream effects become. The heat accumulates, the dryness deepens, the fuel dries out, and right now the center of that blocking pattern, the bullseye of this superheated stalled ridge, is sitting over the American Southwest. Specifically over a region that, even on its best days, is not known for meteorological restraint. The desert Southwest is where the story goes from unusual to something that requires a different vocabulary entirely. Because what is happening there right now, on the thermometers and at the weather stations, has started breaking limits that were not supposed to be breakable in March. Part 4, Ground Zero, the Southwest is breaking limits. 102 degrees Fahrenheit, in Woodland Hills, California, in March. Let that anchor itself for a moment. Woodland Hills is a neighborhood in the San Fernando Valley, the inland basin tucked behind the mountains north of Los Angeles. It is not a desert outpost, it is a suburban community. And on what was essentially the first full day of spring, it recorded 102 degrees, matching or exceeding all-time March temperature records for that location, across the Coachella Valley and the broader inland regions of Southern California and the desert Southwest. Temperatures ranged from 100 to 108 degrees during the peak of this event. To understand why those numbers are so significant in March, you need to understand a basic principle of solar geometry. In March, the sun is still relatively low in the sky compared to summer. The days are roughly equal in length to the nights. The solar angle means that each square foot of ground receives less direct sunlight per hour than it would in June or July. In a normal year, this geometric reality acts as a natural ceiling on March temperatures. The sun simply cannot deliver enough energy in a short enough time window to push temperatures into the range we typically associate with peak summer. Except, apparently it can, under the right atmospheric conditions. What those conditions look like in practical terms is this. A stationary blocking ridge eliminates cloud cover entirely. Clear skies maximize solar radiation reaching the surface. The air is extraordinarily dry, which means there is no moisture in the atmosphere to absorb incoming solar energy before it reaches the ground. Add to that the physical geography of inland valleys and basins, which trap heat through a process called compressional heating, where air descends from surrounding mountains, compresses and warms at a rate of approximately 5.5 degrees Fahrenheit for every 1,000 feet of descent, and you have a system that is actively manufacturing heat from multiple sources at the same time. The sun, the dry air, the descending winds and the terrain are all working in concert. That concert is what pushed Woodland Hills to 102 in March. Cities amplify this further through what is called the urban heat island effect. Pavement, rooftops, concrete and buildings absorb heat during the day and release it slowly at night. They act like a thermal battery, storing solar energy and discharging it over hours. In normal weather, this effect adds a few degrees to urban temperatures compared to surrounding rural areas. During an extreme heat event with maximum solar input and zero cloud cover, the urban heat island effect can add 5 to 10 degrees on top of an already exceptional ambient temperature. The city becomes a furnace within a furnace, and then there are the nights. Overnight low temperatures in parts of the desert Southwest have been staying in the 80s, in March. This is deeply abnormal, and it matters more than most people realize. Human physiology, animal biology, and even building materials depend on nighttime cooling to recover from daytime heat stress. When the overnight low is in the 80s, there is no recovery window. Each successive day begins at a thermal disadvantage, building on the unshaved heat from the day before, compounding, accumulating. The body that did not cool down overnight starts the next day's heat exposure already compromised. This is how heat waves kill people, not just through peak afternoon temperatures, but through the sustained overnight heat that eliminates the body's ability to reset. From a records perspective, what is happening in the Southwest this week is challenging documented all-time March heat records for the United States. Not just records for individual stations, all-time March records. the kind of records that represent the absolute ceiling of what has ever been observed in that calendar month since systematic weather observation began, and the all-time March records are being challenged before the meteorological peak of the event. But here is the pivot point, the pivot that changes this from a story about hot temperatures into a story about genuine, immediate physical danger. Because heat alone, as catastrophic as it is, does not cause the particular kind of disaster that is currently being assembled across the Great Plains and the interior West. Heat alone breaks records. Heat alone is dangerous. But heat plus something else, heat plus a very specific combination of atmospheric factors, creates something far more violent, and that something else has been building quietly while everyone was looking at the thermometer. Part 5. The fire setup is the real threat. Humidity levels across parts of Kansas this week dropped to 5 and 6%. The Sahara Desert, the most iconic expanse of parching dry air on Earth, averages relative humidity around 25%. 5 and 6% is not just dry. It is categorically, physically, dangerous to breathe dry. It is the kind of air that cracks the skin of your lips in minutes. It is the kind of air that pulls moisture out of plants, out of soil, out of every organic surface it touches, relentlessly and continuously. And it has been sitting over tens of millions of acres of grassland for multiple days in a row. Fire weather is not just about temperature. This is a crucial distinction that most coverage of heat waves misses entirely. Temperature is one ingredient in a fire risk equation that has 4 essential variables: heat, wind, humidity, and fuel. Remove any one of those 4 and the fire risk drops dramatically. When all 4 are at extreme values simultaneously, the result is not additive. It is exponential. The risk does not go up by 4, it goes up by something closer to 4 squared, because each element amplifies the effect of the others in ways that create feedback loops. Wind speeds across the Great Plains this week have been reaching sustained velocities of 30 to 40 miles per hour, with gusts higher than that. Wind does several things to fire simultaneously. It dries out fuel faster than ambient humidity alone would. It pushes the fire front forward at the same speed as the wind, dramatically increasing the rate at which fire spreads across a landscape. It supplies fresh oxygen to the combustion process, intensifying the heat of the fire itself, and it can carry burning embers miles ahead of the fire front, starting new ignition points far beyond the visible flames. A fire pushed by 40-mile-per-hour winds is not a fire you can outrun on foot. In some documented cases, it is not a fire you can outrun in a vehicle. The fuel in this equation is the grassland of the Great Plains. After a winter that did not deliver the soil moisture that would normally temper early spring dryness, those grasses are at critically low moisture levels. The technical measurement that fire behavior analysts use is called the Energy Release Component, or ERC. The ERC measures the cumulative dryness of fire fuels, accounting for multiple days of drying conditions, and predicts how intensely a fire would burn given an ignition. ERC values in parts of the Great Plains this week have been in extreme or critical ranges, and crucially the ERC keeps climbing each successive dry day. Day 3 is more dangerous than day 1, not because the day itself is worse, but because the fuel has now been drying continuously for 72 hours. Think of it like this. Imagine you're trying to light a campfire with wood you cut this morning. That wood is still moist on the inside, and lighting it takes effort and patience. Now imagine you cut that wood 3 weeks ago and left it in the sun and wind. It ignites with a single match. The grasslands of Kansas and Oklahoma and Texas and Colorado right now are that 3-week-old wood. They have been curing in 5% humidity and 40-mile-per-hour wind for multiple consecutive days. The ignition energy required to start a fire has dropped close to zero. An electric spark from a power line, a piece of machinery, a cigarette, a glass bottle catching sunlight, any of these sources that exist in abundance across an inhabited agricultural landscape, are sufficient. The National Weather Service has issued red flag warnings across enormous swathes of the Great Plains. A red flag warning is a formal declaration that critical fire weather conditions exist, meaning that any ignition has a high probability of resulting in a large, rapidly spreading fire that challenges or exceeds suppression capabilities. It is not a precautionary advisory, it is an operational alert to emergency responders. When you see a red flag warning covering an area the size of multiple states simultaneously, that is not routine. That is the fire management system telling you it is stretched. March 21st of this year is being identified by meteorologists as the peak convergence day for this fire weather event. The heat at its maximum, the dryness at its deepest, the winds at their strongest, all of it aligned over a region that has been described, in plain language, as ready to ignite. The atmosphere has now assembled every ingredient for catastrophic wildfire ignition. It found the driest place it could. It brought the hottest air it had available in March. It added the wind to carry the fire and dry the fuel even faster. And it eliminated the overnight recovery period that might otherwise have allowed some moisture to return to the vegetation. Everything that could go wrong with fire weather has gone right at the same time. The system is primed. But the real mystery, the question that keeps atmospheric scientists reaching for their datasets, is why this system is behaving this way to begin with. Because the conditions we have described so far are the symptoms. The cause runs deeper, and the cause involves something that weather forecasters have been quietly grappling with for years, something that goes to the heart of how we predict the future in a climate that may be changing faster than our models can track. Part 6. Why the models keep missing. The underforecasting trend deserves more scrutiny than it is getting. Let's go back to the model drift problem we introduced at the beginning, because it is not just a curiosity, it is a symptom of something structural. When meteorologists notice that their models are consistently underestimating observed temperatures in an event like this, their first instinct is to look for physical mechanisms that the models might be poorly representing, and there are a few strong candidates, each of which is measurable and real. The first is compressional heating, which we touched on briefly in the context of inland valley temperatures. When air flows down the eastern slopes of mountain ranges, it descends from higher altitudes to lower ones. As it descends, the atmospheric pressure around it increases and the air compresses. Compression generates heat. The rate at which this happens under dry conditions is called the dry adiabatic lapse rate, approximately 5.5 degrees Fahrenheit for every 1,000 feet of descent. When you have air descending from the Rockies into the Great Plains and into the inland basins of California simultaneously during an event when the overall atmospheric temperature is already elevated, the compressional heating can add meaningful degrees to surface temperatures that models sometimes underweight due to resolution limitations. The second mechanism is the role of clear skies and maximum solar radiation. Models parameterize cloud cover and solar input using formulas derived from historical conditions. Under normal circumstances, those parameterizations are accurate. But during an extreme ridge event with near zero cloud cover over a multi-day period, the actual solar radiation reaching the surface can exceed model assumptions, because those assumptions were built using historical data in which complete cloud-free conditions over large areas for multiple consecutive days were relatively uncommon. Put another way, the model was not trained on enough examples of this kind of sky. And that brings us to the deeper issue. Weather models are not just mathematical physics engines. They are systems that were trained and calibrated on historical observations. The parameters inside them, the coefficients and correction factors that make them accurate, were tuned using decades of atmospheric data. That data describes a specific range of atmospheric behavior. If the atmosphere begins operating more frequently in the tail ends of its statistical distribution, in the 99th percentile territory we described earlier, the historical training data contains relatively few examples of those states. The model's representation of extreme ridge behavior may simply be underfit, not because the physics are wrong, but because the examples used to calibrate the parameters were not extreme enough to prepare the model for what the atmosphere is now producing. The National Weather Service has acknowledged in operational discussions this week that forecast models underperformed on temperature prediction during this event. This is not a scandal. It is not a crisis of confidence in meteorology. It is an honest acknowledgement that the models are operating at the edges of their training distribution, and that when they do, they tend to underestimate rather than overestimate. The atmosphere does not conveniently underperform when the models are wrong. It consistently overperforms. There is a hypothesis, not yet validated at the level of peer-reviewed scientific consensus, but increasingly discussed in operational meteorology circles, that extreme ridging events of the kind we're seeing now may be systematically underrepresented in the historical climate datasets used to train and calibrate models. If the frequency of extreme ridging has increased in recent decades, then the most recent historical data describes more examples of this behavior, but the older data, which often carries significant weight in long baseline model calibration, describes fewer. The model's average includes both periods, and the average underestimates the new reality. Are our models lagging behind real-world climate shifts? That is not a rhetorical question. It is a technical one with serious operational implications, because the answer determines whether the underforecasting we are seeing right now is a quirk of this particular event or a systemic pattern that will affect every major heat event forecast for the foreseeable future. And if it is systemic, then every heatwave warning you see issued in the next decade may be systematically low. The stated high might be the floor, not the ceiling. But even the underforecasting story does not fully explain one of the most important characteristics of this event: its persistence, the fact that it is not moving, the fact that it is sitting in place and accumulating. To understand that, you have to go upstream in the atmosphere, all the way up to the mechanism that should be moving this system along. And that mechanism has been behaving strangely for some time now. Strangely enough that scientists have a name for it. Part 7. The jet stream that refuses to move. The jet stream is supposed to move things along. That is its fundamental job, stated in the simplest possible terms. High-pressure systems, heat waves, cold snaps, storm systems, frontal boundaries, all of the major actors in the atmospheric drama that produces daily weather across the middle latitudes of the planet, they all ride the jet stream the way packages ride a conveyor belt in a distribution warehouse. They develop somewhere upstream, they intensify as conditions favour them, and then the conveyor belt carries them eastward and eventually downstream, away from the region they have been affecting, before they can accumulate enough consequence to become genuinely catastrophic. The reason a typical heat wave lasts 3 to 5 days rather than 3 to 5 weeks is not because the physics of heat dissipation work that quickly. Left to their own devices, a pool of superheated air over a continental interior would take considerably longer than 5 days to mix and cool through natural processes alone. The reason heat waves end on the timescale they do is because the jet stream eventually does its job. It carries the pattern downstream, it breaks the ridge, it allows the cooler air sitting on the other side of the atmospheric fence to reclaim the territory the ridge has been holding. The conveyor belt keeps moving, and moving means the extremes are transient. What is happening with this event, as with a growing list of notable extreme weather events over the past 15 to 20 years, is that the conveyor belt has slowed down. Not stopped entirely, not reversed, but slowed in a way that changes everything about the downstream consequences. The ridge sitting over the western and central United States right now is not moving the way the models initially suggested it would. It is not progressing eastward on the schedule that normal atmospheric dynamics would predict. It is blocking. And blocking, in the technical language of atmospheric science, refers to something very specific. A high-pressure system that has parked itself over a region and is actively resisting the normal eastward progression of weather patterns, deflecting the jet stream around itself rather than being carried along by it, persisting in place for days or weeks beyond what the background flow should allow. Blocking events are not new phenomena. They have always been part of the atmospheric repertoire. The meteorological literature contains documented blocking events going back as far as systematic weather observation allows. They are a known feature of the mid-latitude atmospheric circulation, products of the non-linear dynamics of large-scale flow that can, under the right conditions, produce stable configurations that resist the perturbations that would normally break them down. The atmospheric science community has studied blocking for decades. It is not a mystery in the sense of being unexplained. What is driving serious and sometimes heated scientific debate right now is a different and more consequential question. Are blocking events becoming more persistent, more frequent, or more intense than the historical record of the past century suggests they should be? And if so, why? The hypothesis that has gained the most traction, though emphatically not unanimous agreement, among atmospheric scientists trying to answer that question is built around a phenomenon called Arctic amplification. The logic of the hypothesis is worth walking through carefully because it connects the behaviour of a river of air in the upper atmosphere to changes happening at the top of the world in ways that are not immediately intuitive. The jet stream's speed, its directional stability, and its resistance to developing the deep meanders that can stall into blocking patterns are all maintained by the temperature gradient between the tropics and the Arctic. Think of it as a pressure differential driving a flow, the way a steep slope drives a fast river and a gentle slope drives a slow, meandering one. A large temperature difference between the warm tropics and the cold Arctic creates a steep atmospheric slope that sustains a strong, narrow, fast-moving jet stream that tends to flow in relatively straight paths across the continent. A smaller temperature difference creates a gentler slope, a weaker jet, one that meanders more dramatically and is more susceptible to developing the stationary wave patterns that produce blocking events. The Arctic has been warming. This is one of the most robustly documented observations in the entire body of modern climate science, supported by surface temperature records, satellite measurements, ocean heat content data, sea ice extent observations, and permafrost monitoring across multiple decades and multiple independent research programs. The rate of Arctic warming, approximately 2 to 4 times faster than the global average depending on the time period and method of measurement, is itself a predicted consequence of the way greenhouse gas forcing interacts with the specific physical characteristics of the Arctic environment, including the ice albedo feedback in which melting sea ice exposes darker ocean water that absorbs more solar radiation than the ice it replaced. The warming is documented. The mechanism is understood in broad terms. The Arctic is, by every available measure, warming faster than the rest of the planet. If the Arctic is warming faster than the tropics, the temperature gradient between them is narrowing. If the temperature gradient is narrowing, the theoretical prediction is a weaker, more meandering jet stream that is more prone to developing the deep stationary waves that produce blocking patterns. This is the Arctic amplification hypothesis as applied to jet stream behaviour, and it has attracted serious scientific attention precisely because its logic is straightforward and its potential consequences are severe. A world in which the jet stream is systematically weaker and more prone to blocking is a world in which extreme weather events of all kinds, heat waves, cold outbreaks, floods, droughts, persist longer over the regions they affect, compounding their consequences in ways that peak intensity alone does not capture. It is essential to be honest about where the science actually stands on this question, because the temptation to present it as settled is strong, and the reality is that it is not. The Arctic amplification hypothesis as a driver of jet stream behaviour has not achieved scientific consensus. It remains an active area of research with genuine disagreement among serious, credentialed atmospheric scientists. Some researchers who have examined the observational record find that the statistical signal supporting increased blocking frequency or duration is weaker than the hypothesis would predict, or that the observed changes fall within the range of natural variability without requiring a systematic long-term trend as an explanation. Others argue that the proposed mechanism, while physically plausible, may be too small in magnitude relative to other drivers of jet stream variability to produce detectable changes in blocking statistics on the timescales we've observed so far. The debate is real. The uncertainty is genuine. Anyone who tells you this question is definitively settled is misrepresenting the state of the science in one direction or the other. What is not subject to meaningful scientific debate is the observational record of consequences. Blocking events that cause persistent extreme weather, heat domes that sit stationary for days or weeks over populated regions, extreme cold outbreaks that stall and linger, flooding events sustained by stationary frontal boundaries that deliver rainfall to the same watershed day after day. These are the categories of weather event that produce the most severe human and economic consequences in the historical record. And the observational record of the past 15 to 20 years contains a collection of examples that is difficult to dismiss as simply the routine expression of normal atmospheric variability. The Russian heatwave of 2010, which killed an estimated 55,000 people and destroyed roughly 1/3 of Russia's wheat harvest, was driven by a blocking pattern that persisted for weeks. The European heatwaves of 2018 and 2019 were driven by blocking ridges that sat over Western Europe through the peak of summer. The North American heat dome of 2021, which pushed temperatures in Portland, Oregon to 116 degrees Fahrenheit and killed hundreds of people across the Pacific Northwest, was caused by one of the most intense and persistent blocking ridges ever recorded in that region. The catastrophic flooding in Western Europe in the same summer of 2021 was caused by a stationary frontal boundary, itself a product of the same blocked atmospheric pattern that was simultaneously producing the heat dome on the other side of the ridge. Persistence is more dangerous than intensity. This principle deserves more prominence in public understanding of weather hazards than it typically receives, because human intuition tends to focus on peak values, the highest temperature, the strongest wind, the most intense rainfall rate, while the damage accumulates through duration. A temperature of 105 degrees for a single afternoon is dangerous for vulnerable individuals. A temperature of 95 degrees sustained for 12 consecutive days, with overnight lows that never drop below 80 degrees, kills far more people across a broader population depletes emergency services, overwhelms cooling center capacity, stresses power grid infrastructure at maximum demand for extended periods, dries out vegetation progressively across expanding areas, and accumulates biological heat stress in human bodies in ways that a single extreme day cannot. The duration multiplies the consequence in ways that peak intensity does not predict. The blocking ridge sitting over the United States right now is not showing strong indications of imminent breakdown. The models that track its evolution have been pushed its departure date further into the future, with each successive model run a pattern consistent with a blocking event that is more robust than the initial forecast suggested, and the longer it sits, the more every downstream consequence compounds. The soil gets drier, the vegetation gets drier, the fire weather parameters worsen with each successive day of poor overnight humidity recovery. The heat stress accumulates in the bodies of people and animals across the affected region, and the millions of acres of grassland that have been curing under 5% humidity and 40-mile-per-hour winds move further along a continuum toward a state that fire scientists describe with a term that is both technical and, once you understand what it means, genuinely difficult to read without a certain quiet dread. Part 8. The fire weather equation. No one talks about. Fire is not a thing. Fire is a process. This distinction matters more than it might initially seem, and it is worth sitting with for a moment before we get into the data, because the way most people mentally model fire is fundamentally wrong in a way that leads them to systematically underestimate how quickly a fire situation can go from manageable to catastrophic. Most people think of fire as an object, a thing that exists in a place, that can be located, approached, and extinguished. Firefighters do not think about fire this way. Scientists do not think about fire this way. Fire is a chemical reaction, specifically the rapid oxidation of organic material in the presence of oxygen and sufficient heat. It is a process, not a thing, and that distinction is the entire difference between understanding fire behavior and being surprised by it. That chemical reaction has precise and non-negotiable requirements. It requires fuel, organic material that can be oxidized. It requires heat, enough thermal energy to initiate and sustain the reaction, and it requires oxygen, the oxidizing agent that the reaction consumes. Remove any one of those three components and the reaction stops. The fire goes out. This three-part framework, known as the fire triangle, is the foundation of everything fire suppression science is built on. Every tool, every technique, every strategy that firefighters deploy against an active fire is an attempt to attack one or more of those three legs. Water attacks the heat leg by cooling the fuel below ignition temperature. Retardant attacks the fuel leg by coating it with a chemical barrier that slows oxidation. Fire breaks attack the fuel leg by creating gaps in the continuous fuel bed that the fire cannot bridge. Foam attacks both heat and oxygen simultaneously. The entire art and science of firefighting, distilled to its essence, is the science of breaking the triangle. What fire weather does, what the specific combination of conditions that has assembled itself across the Great Plains and the interior West this week does, is make all three legs of the triangle simultaneously harder to attack, while simultaneously making the reaction more vigorous, more energetic, and more resistant to suppression efforts. When the heat is extreme, the fuel is already pre-warmed before ignition occurs, meaning the reaction starts faster and burns hotter from the first moment. When the humidity is at 5 or 6%, the fuel has been stripped of the moisture that would otherwise absorb heat during combustion and slow the reaction. When the winds are at 30 to 40 miles per hour, fresh oxygen is being continuously delivered to the reaction zone at a rate that overwhelms the fire's own consumption, and the heat generated by combustion is being pushed forward into unburned fuel ahead of the fire front, preheating it toward ignition temperature before the flames even arrive. Every leg of the triangle is being actively reinforced by the atmospheric conditions. Every tool available to suppress the fire is being actively undermined by those same conditions. Let's spend serious time on the fuel leg, because it is the one that most fire coverage underexplains and most people most significantly underestimate. The instinct when hearing that humidity is at 5% is to think dry, very dry, dangerously dry. That instinct is correct as far as it goes, but it does not go nearly far enough because it treats the dryness as a static condition rather than a dynamic process. The dryness is not just a state, it is an ongoing extraction, It is the atmosphere actively pulling moisture out of every organic surface it contacts, continuously, without pause, driven by the enormous gradient between the near-zero moisture content of the air and the higher moisture content of the vegetation it surrounds. Vegetation does not ignite instantly. It has to be prepared for combustion through a process called fuel curing, and that process operates on a timeline that most people never consider. Living plant cells contain water, and that water must be driven off before the plant tissue will combust reliably. The energy required to drive off that moisture is energy that cannot go into sustaining the combustion reaction, which is why freshly cut green wood is difficult to burn and thoroughly dried wood ignites with a match. The drying process that converts living vegetation from resistant to ignition to ready to burn takes time, and the rate at which it proceeds depends on the temperature, the wind speed, and most critically, the relative humidity of the surrounding air. Here is the part that most fire weather coverage misses entirely, the part that makes the difference between a serious fire risk on day 1 of a low humidity event and a catastrophic fire risk on day 3. The drying is not linear. It does not proceed at a constant rate from the surface inward. On the first day of extreme low humidity, the drying primarily affects surface fuels, the fine grasses, dead leaves, and small twigs at the top of the fuel bed. These are the lightest and least dense materials, and they lose moisture quickly. But they are also the smallest contributors to the total energy release when a fire burns through them. They ignite easily and burn fast, but they do not sustain a fire the way denser fuel does. By day 2, if the humidity remains critically low, the drying has penetrated deeper into the fuel bed, reaching the stems of grasses and the smaller branches of shrubs. These are denser materials that hold more moisture and release more energy when they burn. By day 3, the drying is reaching fuel that was protected by its own density and by the moisture held in the layers above it. Root crowns, the bases of grass stems, the structural material of perennial plants that normally maintains higher moisture content even through dry periods. That material, when it dries and ignites, burns hotter and longer than surface material. It sustains a fire through conditions that would extinguish a fire burning only surface fuels. The energy release component, the metric that fire behavior analysts use to estimate how intensely a fire would burn given an ignition, builds not just because each day adds to the total drying, but because each successive day the drying is reaching fuel with greater energy content per unit weight. Day 3 of a critical fire weather event is not simply 3 times more dangerous than day 1. It is categorically more dangerous, in ways that the linear intuition most people apply to these situations does not capture. Then there is the overnight recovery problem, which is one of the most operationally significant and least publicly discussed factors in multi-day fire events. Under normal atmospheric conditions, when a hot dry day gives way to a cooler night, relative humidity rises. As temperatures drop, the atmosphere's capacity to hold water vapor decreases, and the relative humidity climbs toward values that allow fine fuels to partially reabsorb moisture from the air. This nightly humidity recovery is not a minor effect. It is the mechanism by which the living landscape partially resets each night, allowing vegetation to recover some of the moisture it lost during the day's heat and dryness. It is also the window during which fire suppression crews make their most significant progress against active fires. The reduction in fire intensity that comes with overnight humidity recovery allows ground crews to approach the fire perimeter, construct containment lines, and establish the fire breaks that will hold when the fire intensifies again the following afternoon. Professional wildfire management strategy is built around the overnight recovery window in ways that most people never see or appreciate because the dramatic footage always comes from the daytime intensity, not the overnight work that makes daytime containment possible. When a blocking pattern keeps overnight low temperatures in the 80s, and when the dry air mass associated with the ridge does not retreat overnight the way it would in a normal weather pattern, the humidity recovery is poor to non-existent. The air at 2 in the morning is still at single-digit relative humidity. The vegetation that should be rehydrating is continuing to lose moisture in darkness. The suppression crews that should be making containment progress are instead working in conditions that remain dangerous, and in fuels that remain critically dry. Each successive dawn begins with a fuel moisture deficit deeper than the dawn before. The cumulative drying effect is geometric rather than arithmetic, accelerating rather than linear, building toward a threshold where a single ignition source, anywhere across an area covering tens of millions of acres, becomes sufficient to initiate a fire that no available suppression force can contain in its early minutes, and the ignition sources are everywhere. This is the final and most sobering element of the fire weather equation, the one that makes the assembled conditions not just dangerous in theory, but inevitable in practice if the window extends long enough. Unlike hurricanes, which develop over open ocean and announce themselves across satellite imagery for days before they make landfall, unlike floods, which require a measurable accumulation of water over time that can be modelled and anticipated, wildfires ignite from a single point source of trivial energy that can occur at any location across the entire affected area at any moment. An electrical arc from a power line swaying in 40-mile-per-hour wind, a spark from a piece of harvesting equipment operating in a dry field, a vehicle with a dragging component striking the pavement on a rural highway, a glass bottle left in a roadside ditch focusing sunlight onto a dried grass stem. The ignition energy required to start a fire under current fuel moisture conditions has dropped so low that sources we normally consider negligible have become operationally significant. We do not know where the ignition will occur. We do not know when. We know only that the conditions for an ignition to become a catastrophe are comprehensively and simultaneously in place across a region the size of several European nations, and then, as if the atmospheric setup were not already sufficient to command every available unit of attention, something else arrived. Not from the plains, not from the ridge of high pressure overhead, from a direction that has nothing to do with temperature or humidity or wind, and from a distance that makes the scale of everything we have been discussing suddenly feel very small. Part 9. The 48-hour convergence window. The Sun launched multiple coronal mass ejections this week, and before you file that under routine space weather news and move on, stay with me for a moment, because the timing of these particular ejections relative to everything else happening on Earth right now is the kind of detail that makes data-minded people set down their coffee and look at the calendar twice. A coronal mass ejection, or CME, is a cloud of magnetized plasma ejected from the Sun's surface during periods of intense magnetic activity. Think of it as the Sun sneezing, except the sneeze is a billion-ton cloud of charged particles travelling at speeds that make the fastest thing humanity has ever built look like it is standing still. These ejections travel through space at speeds ranging from roughly 100 miles per second on the slow end to over 5,000 miles per second during the most energetic events. At those velocities, a fast CME can cover the 93 million miles between the Sun and Earth in as little as 15 to 18 hours. A slower one might take 2 to 3 days. Either way, when one is pointed at us, the clock starts the moment it leaves the solar surface. When a CME reaches Earth and interacts with the magnetosphere, the invisible magnetic field that surrounds and protects our planet, the result is called a geomagnetic storm. The magnetosphere is remarkable in ways we rarely appreciate. It is the reason Earth has life and Mars does not, at least in part. It deflects the continuous stream of charged particles flowing outward from the Sun, the solar wind, away from the surface. Without it, that radiation would strip away the atmosphere over geological time and bombard the surface with levels of energy incompatible with complex biology. The magnetosphere is not dramatic, it is quiet. It does its job every single second of every single day without announcement, until a CME arrives, and then it has to work considerably harder. The Space Weather Prediction Center, which is the United States government agency responsible for monitoring and forecasting space weather events, categorizes geomagnetic storms on a scale from G1 to G5. G1 is minor, G5 is extreme, the category reserved for events like the legendary Carrington event of 1859, which was powerful enough to set telegraph wires on fire and produce auroras visible from the tropics. The CMEs launched from the Sun this week, based on data from NASA monitoring systems and ongoing assessments from the Space Weather Prediction Center, are projected to arrive within the same general time window as the peak of the heat and fire weather event currently affecting the United States. Initial assessments have placed the potential geomagnetic storm category at G2 to G3, moderate to strong. At the G2 to G3 level, the documented and confirmed effects on Earth are real and worth understanding clearly. Enhanced aurora visibility at mid-latitudes is the most visible and photogenic effect, the kind that fills social media with green and purple sky photographs from places like Minnesota and Montana that do not usually see the northern lights. But beyond the visual spectacle, there are operational consequences. Possible intermittent disruptions to satellite orientation and GPS signal accuracy, potential stress on certain high-latitude power grid components, specifically the large transformers that manage long-distance power transmission, disruptions to some radio communications, particularly high-frequency radio used by aviation and emergency services. These are real, measurable, documented effects at that storm level. They are also, in normal circumstances, manageable. Grid operators have protocols, satellite operators have safe modes, aviation has contingency communication systems. The world has dealt with G2 and G3 storms before and will deal with them again. Now let's be precise about what the science says and, equally importantly, what it does not say. There is no established, peer-reviewed, scientifically validated causal mechanism linking geomagnetic storms to surface weather on Earth. None. No credible atmospheric scientist has proposed a model in which a G2 or G3 geomagnetic event meaningfully raises surface air temperatures, intensifies a blocking ridge, reduces relative humidity over the Great Plains, or increases wind speeds over fire-prone grasslands. The heat dome sitting over the American West right now is a product of atmospheric dynamics. Full stop. The fire weather setup is a product of those same atmospheric dynamics, combined with land surface conditions that have been building for weeks. The CME arrival is a solar physics event governed by processes happening 93 million miles away that have no known direct line of influence on whether Kansas is at 5% humidity or 15% humidity. These are separate systems. Treating them as causally connected would not be responsible science communication, and we're not going to do that here, and yet. The timing is what it is, and the timing is worth sitting with for a moment before we move on. A peak heat event, with temperatures challenging all-time March records across the American Southwest. A peak fire weather event, with red flag warnings covering tens of millions of acres of critically dry fuel across the Great Plains, and a moderate to strong geomagnetic storm arrival, projected to land within the same approximately 48-hour window as the meteorological peak of both. 3 separate systems, 3 separate physical causes, 1 narrow window of time. From a pure infrastructure perspective, the convergence carries genuine operational weight that grid managers and emergency planners are actively tracking. Geomagnetic storms can induce currents in long-distance power transmission lines, currents that stress transformers in ways that are manageable under normal load conditions, but become more consequential when the grid is simultaneously running at maximum capacity. During an extreme heat event, power demand is at its absolute ceiling. Every air conditioning unit in the affected region is running continuously. Industrial cooling systems are at full load. The grid is not operating with reserve margin. It is running close to its limits before any additional stress is applied. The combination of maximum grid demand and moderate geomagnetic stress on transmission infrastructure is not a theoretical concern. It is a real operational variable that utilities in the affected regions are watching closely and preparing for. There is also the firefighting dimension, which receives almost no attention in standard space weather coverage. Satellite-based fire detection systems, which use thermal infrared sensors aboard Earth-observing satellites to identify new ignitions and track fire perimeters in near real time, can experience degraded accuracy during periods of elevated geomagnetic activity. GPS navigation systems used by aerial firefighting assets, the air tankers and helicopters that make precision drops on active fire lines, rely on satellite signals that can be disrupted by ionospheric disturbances associated with geomagnetic storms. Small disruptions to those systems during peak fire weather operations, when the fire environment is at its most dangerous and the margin for error in aerial operations is at its smallest, are not trivial. They do not make the situation catastrophic, but they add friction at precisely the moment when friction is least affordable. The data is the data. The convergence is factual and documented. The causal interpretation requires rigor, and rigorous analysis does not support drawing direct physical connections between the space weather event and the atmospheric event. What rigorous analysis does find is that coincidences of timing between separate Earth systems and space weather events are more common than most people realize, in part because we tend to notice them more during extreme events, when our attention is already elevated. Confirmation bias is a real, cognitive phenomenon, and it operates most powerfully when we are already primed to find patterns. We should report the convergence honestly. We should not manufacture a physical connection that the physics does not support. But here is the thing, this is not the only unusual event in this same 48-hour window. And when you step back from the heat dome and the fire weather and the incoming geomagnetic storm and look at the full inventory of events occurring simultaneously during this same narrow period, the list starts to require a more careful word than coincidence. Not because the individual items are connected, they almost certainly are not in any way that current physics can describe. But because the sheer density of anomalies compressed into a single week across multiple independent physical systems is the kind of pattern that deserves documentation, sober examination, and the kind of honest curiosity that neither reaches for easy explanation nor reflexively dismisses the question. Something unusual is happening across multiple domains simultaneously. The data says so, and the next item on that list is the one that arrived without warning, from above, over the American Midwest and lit up the sky in broad daylight. Part 10. Stacked Anomalies. Coincidence or pattern? Something fell over Ohio this week, not metaphorically, not as a headline exaggeration. Something physical, travelling at extraordinary velocity, entered the atmosphere over the Midwestern United States and released enough energy to be detected across multiple states simultaneously. A fireball, confirmed by monitoring networks operated by institutions that track exactly these kinds of events, entered the atmosphere with an estimated energy release equivalent to approximately 0.37 kilotons. That number needs context, because kilotons is a unit most people associate with nuclear weapons and not with Tuesday mornings over the American Midwest. The bomb dropped on Hiroshima in 1945 had a yield of approximately 15 kilotons. The Ohio fireball released energy roughly 40 times smaller than that. In the context of nuclear weapons, that gap is enormous and reassuring. But in the context of natural atmospheric events, 0.37 kilotons is not a footnote. It is a significant bolide entry. A bolide, for those unfamiliar with the term, is a particularly bright and energetic meteor, one that releases enough energy during its atmospheric entry to produce visible light, a detectable pressure wave, and infrasound signatures that propagate hundreds or even thousands of miles from the point of entry. The Ohio event was detected by infrasound sensors, reported by hundreds of eyewitnesses across multiple states, and confirmed by the monitoring networks that exist specifically to document events of this kind. This was not a rumour. It was not a misidentified aircraft or a social media exaggeration. It was a real object, arriving from space, releasing real energy over a populated region of the United States. To understand what that entry looked like physically, consider what happens when a rocky or metallic object, travelling at somewhere between 25,000 and 160,000 miles per hour, encounters an atmosphere. The object does not simply slow down. It compresses the air in front of it so rapidly and so violently that the compressed air heats to temperatures that can exceed 50,000 degrees Fahrenheit, several times hotter than the surface of the sun. The object itself begins to ablate, shedding material in a trail of superheated plasma. From the ground, this looks like a streak of brilliant light, often brighter than the full moon, sometimes bright enough to cast shadows in daylight. The pressure wave generated by the supersonic passage through the atmosphere propagates outward as a sonic boom that can rattle windows and trigger car alarms across a wide area. When the object or its fragments reach a low enough altitude or fully disintegrate, the terminal explosion releases the bulk of its kinetic energy as a pressure pulse that infrasound sensors can detect at continental distances. The Ohio fireball did all of this, and it did it during a week that was already running well above its anomaly quota, because here is the inventory of what was happening in the same approximate time window. A magnitude 6.6 earthquake occurred near Antarctica, a seismically active region, but one whose events rarely make the news cycle. Kilauea volcano in Hawaii continued elevated eruptive activity, maintaining the kind of sustained output that volcanologists monitor carefully for signs of escalation. Multiple coronal mass ejections launched from the sun in succession, directed toward Earth and projected to arrive within a narrow window. A significant geomagnetic storm period opened over Earth as a result, affecting high-latitude infrastructure and producing aurora activity at unusually low latitudes. And a record-breaking heat dome sat stationary over the western and central United States, with fire weather conditions at critical levels across tens of millions of acres of fuel that had been drying for multiple consecutive days. One event in that list would be a story. 2 would be a coincidence worth noting. 5, compressed into roughly 48 hours, starts to feel like something that deserves a more careful kind of attention. Now here is the moment that requires intellectual honesty, the kind of honesty that is harder to maintain when a list like the one above is sitting in front of you. Scientific discipline requires stating clearly and without hedging. These events represent independent physical systems. Earthquakes are driven by the slow accumulation and sudden release of stress along tectonic plate boundaries, a process governed entirely by the dynamics of Earth's lithosphere and operating on timescales of decades to centuries. Volcanic eruptions are driven by the accumulation of magmatic pressure in subsurface chambers, a process governed by the density and composition of molten rock and the structural integrity of the overlying crust. Atmospheric heat waves are driven by atmospheric dynamics, specifically the behavior of pressure systems, jet stream patterns, and the thermodynamics of the lower atmosphere. Bolide events are driven by the orbital trajectories of near-Earth objects, trajectories that were set in motion millions or billions of years ago by gravitational interactions in the early solar system, and have been evolving on their own inertia ever since. Geomagnetic storms are driven by solar physics, by the magnetic field dynamics of a star 93 million miles away. There is no known causal mechanism linking any of these systems to the others. None. Not a partial mechanism, not a theoretical pathway under investigation. None. The science does not support a unified explanation, and stating otherwise would be irresponsible. But here is the equally honest other side of that statement, the side that intellectual rigor also requires acknowledging. Human beings are extraordinarily good at detecting patterns. This cognitive tendency has a name in psychology: apophenia, the perception of meaningful connections between unrelated things. It is often framed as a cognitive bias to be identified and corrected, a flaw in our otherwise useful pattern recognition hardware. And sometimes that framing is exactly right. Sometimes the perceived pattern is noise, and the responsible thing is to say so clearly and move on. But sometimes, not always, not even often, but sometimes, the pattern detection instinct is pointing at something worth examining more carefully, not because the individual events are causally connected, but because their simultaneous occurrence in a narrow window is a genuine statistical question worth asking rigorously. When multiple independent physical systems all exhibit anomalous behavior during the same time period, the honest scientific question is, what is the probability of that occurring by chance? And the honest answer is that calculating that probability requires knowing the baseline rate of anomalous behavior in each system independently, and we do not always have reliable baseline rates for every type of extreme event. Some of these systems have been monitored with modern instrumentation for only a few decades. The historical record is short. The statistics are genuinely uncertain. There is also a subtler issue. Our detection and reporting of extreme events has improved dramatically over the past 20 years. We have more seismometers now than we did in 2005. We have better bolide detection networks. We have continuous solar monitoring from spacecraft that did not exist a generation ago. More sensors means more detected events, which means any given week in 2026 will contain more documented anomalies than the equivalent week in 1990 simply because we are looking harder and with better instruments. Some portion of what feels like an increase in stacked anomalies is genuinely an increase. Some portion is improved detection. Separating the two is one of the more technically demanding problems in observational science. The framing that serves us best when confronting a week like this one is neither credulous nor dismissive. It is curious. Genuinely, carefully, methodically curious. Something unusual is happening across multiple physical domains in the same narrow window of time. The atmospheric component, the heat dome, the fire weather setup, the model underperformance, has explanations that are reasonably well understood and documented. The bolide over Ohio has a straightforward physical explanation. A rock from space entered the atmosphere and burned. The earthquake near Antarctica fits within known patterns of seismic activity in that region. The volcanic activity at Kilauea is part of a longer eruptive sequence. The geomagnetic storm is the product of solar activity during a well-documented active phase of the solar cycle. Each item on the list has an explanation. What does not have an explanation, or more precisely, what does not require one but remains worth documenting, is their compression into the same week. The stacking of anomalies across independent systems is the kind of observational signal that deserves careful documentation and sober analysis, not breathless narrative connection, and not reflexive debunking driven by discomfort with the question. The data shows what it shows, and what it shows is that this is a week of exceptions, distributed across multiple systems, arriving simultaneously. We do not have a unifying explanation. We may never have one, because one may not exist. But we do have a pattern, and patterns in data are where every serious scientific question begins. The next layer of context for understanding this particular pattern sits not in the atmosphere, not in the crust beneath our feet, not even in the near-Earth environment where the Ohio fireball briefly announced itself. It sits 93 million miles away, in the star that has been the engine of every system we have discussed tonight. Because the Sun is not behaving the way the models predicted it would. And that story, the story of a solar cycle that surprised the people who study it for a living, turns out to connect to almost everything else. Part 11. The Sun is entering a more violent phase. The Sun operates on a clock, not a metaphorical clock, not a poetic device. A real, measurable, physically driven cycle of magnetic activity that has been ticking for as long as the Sun has existed, roughly 4.5 billion years, and that astronomers have been formally documenting since the mid-19th century. The cycle runs approximately 11 years from start to finish, moving from a period of relative calm called solar minimum through a period of intense and increasingly unstable magnetic activity called solar maximum, and then declining back toward minimum before the whole sequence begins again. It is one of the most consistent and well-documented periodic phenomena in all of astrophysics, and like all clocks, it is useful precisely because it is predictable, except that right now the clock is running fast, and it is running loud. To understand what that means in practical terms, it helps to understand what the Sun actually looks like at different phases of its cycle. During solar minimum, the Sun's visible surface, the photosphere, is relatively featureless. Sunspots, those dark regions of intense localized magnetic field that appear as cooler patches against the brighter surrounding surface, are rare or absent. The solar wind, the continuous stream of charged particles flowing outward from the Sun in all directions, blows at relatively steady and moderate velocities. Coronal mass ejections are infrequent. From a space weather perspective, solar minimum is the Sun at its most cooperative. It is still an active star. It is still producing radiation and solar wind continuously. But it is not particularly disruptive to the technological infrastructure of the small blue planet orbiting it at 93 million miles. Solar maximum is a different environment entirely. As the cycle progresses toward its peak, the Sun's internal magnetic field undergoes increasing complexity and instability. Sunspots appear in growing numbers, often in clusters, forming what are called active regions. These active regions are sites of intense magnetic stress, areas where magnetic field lines of opposite polarity are forced into close proximity by the churning motion of the solar plasma beneath them. That magnetic stress builds until it resolves suddenly and violently, snapping and reconnecting in a process called magnetic reconnection that releases enormous amounts of energy in a fraction of a second. When that energy release is primarily electromagnetic radiation, it is called a solar flare. When it launches a billion-ton cloud of magnetized plasma into space, it is called a coronal mass ejection. During solar maximum, these events can occur multiple times per week. The Sun, to use the most accurate word available, becomes restless. We are currently in solar cycle 25, and it has genuinely surprised the solar physicists who study these cycles for a living, which is itself a notable data point, because solar physicists are not easily surprised by the Sun. When solar cycle 25 began its rise around 2019 and 2020, the forecasting panel convened by the National Oceanic and Atmospheric Administration and NASA projected that it would be a relatively moderate cycle. The basis for that projection was reasonable. The two preceding cycles, solar cycles 23 and 24, had been below average in intensity, part of what some researchers described as a grand solar minimum tendency in the early 21st century. The expectation was that solar cycle 25 would continue that subdued trend, producing a modest maximum and a relatively quiet period of space weather. The forecast was wrong, not slightly wrong, significantly wrong. Solar cycle 25 accelerated faster than predicted, produced more sunspots than the forecast suggested, and reached activity levels that exceeded the projected maximum by a meaningful margin. The solar maximum for this cycle was reached sometime around late 2024 and early 2025, earlier and at higher intensity than the consensus forecast had indicated. The Sun is currently in the declining phase from that peak, moving back toward the quieter conditions of solar minimum. But here is the important operational detail. The declining phase of a solar cycle is not a rapid shutoff. Solar activity can remain elevated, producing significant flares and CMEs for months to years after the technical maximum has passed. We are not in the clear simply because the peak is behind us. The Sun is still restless. The CMEs arriving this week are evidence of that. More active Sun means more sunspots. More sunspots means more active regions. More active regions means more opportunities for the magnetic stress events that produce flares and coronal mass ejections. The CMAs arriving this week are consistent with an active Sun operating in the post-maximum but still elevated phase of solar cycle 25. They are not the largest CMEs the Sun can produce. The most extreme geomagnetic storms, the G5 category events, require CMAs of extraordinary speed and magnetic field strength that are relatively rare even during solar maximum conditions. What is arriving this week sits in the G2 to G3 range, moderate to strong, notable, operationally significant for infrastructure managers, but within the range of events that modern space weather response systems were designed to handle. And yet, the historical record contains a data point that should permanently recalibrate anyone's sense of what the Sun is capable of, and why the difference between G3 and G5 is not a matter of degree, but a matter of civilizational consequence. The Carrington event of 1859 remains the benchmark against which all geomagnetic storms are measured. It was caused by one of the most powerful CMEs in recorded history, launched from a large active region on the Sun's surface and directed almost perfectly toward Earth. The CME travelled the distance from Sun to Earth in approximately 17 hours, which is extraordinarily fast and indicates an ejection velocity near the upper end of what the Sun can produce. When it struck Earth's magnetosphere, the resulting geomagnetic storm was so intense that auroras were visible as far south as the Caribbean Sea and as far north as the southern tips of South America and Australia. People in the northeastern United States reported being able to read newspapers by the light of the aurora at midnight. The effects on the technology of 1859 were dramatic and, in retrospect, darkly instructive. Telegraph wires across North America and Europe sparked spontaneously, delivering electric shocks to operators who had not touched their equipment. Some telegraph systems caught fire, others, in a detail that sounds almost impossible, continue to operate without any connection to their power sources, driven entirely by the geomagnetically induced currents flowing through the wires from the storm itself. Operators reported being able to send and receive messages using only the aurora's energy. In 1859, the sum total of electromagnetic infrastructure vulnerable to geomagnetic storms was the telegraph network, a system of wires that, while economically important, was not load-bearing for the survival of cities or the functioning of hospitals or the movement of food through supply chains. Were an equivalent event to occur in 2026, the inventory of vulnerable infrastructure would be unrecognizable by comparison. Power grids serving hundreds of millions of people, grids whose long-distance high-voltage transmission lines act as antennas for geomagnetically induced currents, would face stress levels that their transformer equipment was not necessarily designed to survive. GPS satellite networks relied upon not just for navigation, but for the precise timing signals that synchronize financial transactions, coordinate cellular networks, and guide precision agricultural equipment, would experience signal degradation or loss across wide areas. Communications satellite systems supporting everything from emergency response coordination to internet access for billions of people would be at risk of orientation loss or electronic damage. The power management systems of every modern city, the automated switching networks that balance load across regional grids in real time, would be operating in a degraded electromagnetic environment at exactly the moment when demand was at its peak due to the concurrent heat event. The probability of a Carrington-scale event occurring in any given year is estimated by space weather researchers at somewhere between 0.1 and 1%. In a single year, that sounds low. Comfortably low. The kind of probability you file under unlikely and do not think about again. But probability does not work that way over time. Over a decade, a 1% annual probability compounds to roughly a 10% cumulative probability. Over 50 years, it approaches 40%. Over a century, the mathematics suggest that a Carrington-scale event is not a question of whether but of when, and we are currently living through the most active phase of the most active solar cycle in 2 decades, with aging grid infrastructure in many regions that has not been comprehensively hardened against geomagnetic storm effects, and with a level of civilizational dependence on electromagnetic systems that has no historical precedent. The CMEs of this week are not Carrington scale. They are manageable, they are being managed. But they are a reminder, arriving at a moment of maximum inconvenience, that the Sun is not a passive backdrop to the events unfolding on Earth's surface. It is an active participant, a variable, one that operates on its own schedule, follows its own rules, and occasionally sends reminders that the distance between us and it is not quite as protective as daily life leads us to assume. And this week, while the heat dome burns and the grasslands dry and the fire weather window peaks, the Sun is contributing its own chapter to a story that keeps adding pages. And somewhere much closer to home, something else is moving through the neighbourhood. Part 12, the next close asteroid pass, March 2026. An asteroid named 2026 FU is going to pass Earth this month. It will not hit us. Let me put that on the table immediately and unambiguously, because the phrase asteroid passing Earth has a way of triggering a very specific kind of anxiety that is worth diffusing before we go any further. 2026 FU poses no impact risk. NASA's planetary defense tracking systems, which monitor near-Earth objects continuously using a global network of ground-based telescopes and space-based observatories, have confirmed this with the kind of orbital precision that leaves no meaningful room for uncertainty. The object will pass. It will continue on its orbital path. It will not return to a threatening geometry in any time frame relevant to anyone reading or watching this. We are safe. That is not a reassurance offered to soften bad news. It is simply the accurate statement of what the data shows. Now, with that established, let's talk about how close it is actually going to get. Because the distance is worth understanding not as a threat, but as a measure of the environment Earth actually moves through every single day. An environment that most people never think about, and that the Ohio bolide earlier this week made briefly, dramatically visible. At its closest approach, 2026 FU will be at approximately 1.5 lunar distances from Earth. 1 lunar distance is the average distance between Earth and the Moon, roughly 239,000 miles. 1.5 times that figure puts 2026 FU at approximately 350,000 miles from Earth at its nearest point. For most people, 350,000 miles sounds like an enormous distance. And by the standards of daily human experience, it is. It is roughly 44 times the circumference of the Earth. It is farther than any human being has ever travelled from home. In the context of a suburban street or a cross-country drive, 350,000 miles is incomprehensibly far. In the context of the solar system, it is something else entirely. The solar system operates at scales that make 350,000 miles feel intimate. Earth orbits the Sun at roughly 67,000 miles per hour. The Moon, our nearest neighbour, sits at 239,000 miles and is considered so close that we have visited it with 1960s technology. Mars, our next-door neighbour in the planetary sense, is typically tens of millions of miles away. The nearest star is 25 trillion miles away. Against those scales, 350,000 miles is, in the most literal sense of the expression, local. It is the distance at which, if space were a highway, you could feel the wind from a passing vehicle. It is a close shave, a notable pass. The kind of approach that planetary defense scientists log carefully and the public would find alarming if they encountered the raw number without context. 2026 FU will pass and continue on its orbital path without incident, but its proximity this month, arriving in the same week as the Ohio bolide entry, during the same period as an active geomagnetic storm window and a record-breaking atmospheric heat event, adds one more item to a list that keeps growing. Not because the asteroid is connected to any of those other events, it is not, but because its presence in the near-Earth environment this week is a concrete illustration of something that is easy to forget in the course of ordinary life. Earth does not travel through empty space. It travels through a populated neighbourhood, and the neighbours are not always at a comfortable distance. The broader discussion of near-Earth objects is worth having in depth, because there is a genuinely interesting observational paradox embedded in the data that has direct relevance to everything we have been discussing throughout this story. The number of near-Earth objects detected, catalogued, and publicly documented has increased dramatically over the past 2 decades. In 1998, there were fewer than 1,000 known near-Earth objects in the catalogues maintained by NASA and international partner agencies. Today, that number has grown to tens of thousands. The rate of new discoveries continues to accelerate as detection systems improve. To someone encountering those numbers for the first time, the natural interpretation might be that space is becoming more crowded, that the population of objects near Earth is growing, that the risk is increasing. That interpretation is almost certainly wrong. What the increasing catalogue numbers reflect is not an increase in the population of near-Earth objects. Those objects have been on their current orbital paths for millions or billions of years. They were there in 1998. They were there in 1950. They were there before the first human being looked up at the night sky and wondered what was moving among the fixed stars. What has changed is our ability to find them. The development of automated wide-field sky survey programs, projects like the Catalina Sky Survey operating out of Arizona, the Pan-STARRS program in Hawaii, and the Atlas Survey System with stations on multiple continents, has transformed the search for near-Earth objects from a manual, targeted hit-or-miss enterprise into a systematic, continuous, algorithmically assisted census. These systems scan the entire accessible sky repeatedly, comparing images taken minutes or hours apart to identify objects whose positions have changed, the signature of something moving through the solar neighbourhood rather than sitting at stellar distances. The result is a catalogue that grows by hundreds of new objects every month, not because the objects are new, but because we are finally looking carefully enough to find them. This distinction matters enormously, and not just for asteroid science. It speaks to a broader principle that runs through everything we have discussed in this video, and that deserves explicit acknowledgement. What often appears to be an increase in the frequency of extreme events may be, at least in part, an increase in our ability to detect, document, and communicate those events. We have more weather stations now than we did in 1950. We have better satellite coverage of remote ocean and land areas that previously had no surface observations at all. We have more seismometers distributed more evenly across the globe, capable of detecting earthquakes that would have been missed entirely by the sparser networks of previous decades. We have more volcanic monitoring infrastructure, more space weather observation satellites, more atmospheric sounding equipment, more lightning detection networks. The sensors are everywhere now in a way they simply were not a generation ago. Some portion of what appears to be an increasing frequency of documented anomalies, whether in weather, seismology, solar activity, or near-Earth object encounters, is genuinely an increase driven by real physical changes in those systems. Climate science has documented real changes in the frequency and intensity of extreme heat events that cannot be explained by improved detection alone. Solar Cycle 25's overperformance relative to forecast is a real phenomenon, not a detection artifact. But some portion of the apparent increase in anomaly frequency is improved detection, and the challenge of separating the genuine signal from the detection enhancement effect is one of the most technically demanding problems facing scientists across multiple disciplines simultaneously. It requires careful baseline correction, accounting for changes in observation network density over time, and rigorous statistical methods that can distinguish a real trend from an observational artifact. It is not easy. It is not always done well, and it is worth keeping in mind every time a headline announces that some category of extreme event is happening more often than ever before. 2026 FU will pass Earth quietly, invisibly to the naked eye, noted in the catalogues and then receding back into the orbital paths that carry it around the Sun on its own schedule. It will not announce itself. It will not affect the heat dome or the fire weather or the geomagnetic storm. It is simply passing through, as objects in the solar neighbourhood have always passed through, noticed now only because we have finally built the instruments good enough to see them. But its passage this week sits alongside something else worth carrying forward from this part of the story. The planetary defence community that tracks objects like 2026 FU, the scientists and mission planners and engineers who work on systems designed to detect, characterise, and if necessary deflect asteroids on dangerous trajectories, are engaged in a specific kind of work that has broader lessons for every other risk discussed in this video. They are doing long-horizon risk management. They are maintaining watch, not because any specific object poses a threat today, But because the cumulative probability of a significant impact over centuries and millennia is mathematically real, and the cost of building and maintaining a detection and response infrastructure is orders of magnitude smaller than the cost of being unprepared when the probability finally resolves into an event, that principle, watch continuously, prepare seriously, act before the emergency rather than during it, applies to space weather preparedness, to wildfire management, to heat infrastructure planning, and to the atmospheric monitoring systems that are currently struggling to keep pace with an atmosphere that is operating beyond its historical parameters. The telescope that found 2026 FU was built before 2026 FU was known to exist. That is what preparation looks like, and as we extend humanity's observational reach beyond the Earth entirely, the next generation of that preparation is already being assembled, pointed not at the ground or even at the nearby sky, but at the sun itself from a vantage point no human being has occupied in more than 50 years. Part 13, Artemis II and the return to deep space. Humanity is about to leave Earth orbit for the first time in more than 50 years. Let that land for a moment, because it is easy to read a sentence like that and let it pass without registering its full weight. 50 years is not an abstract interval. It is longer than the entire history of powered aviation was when Apollo 11 landed on the Moon. It is long enough that every human being alive today who was not yet born in 1972, which is to say the overwhelming majority of the living human population, has spent their entire existence on a planet whose species had not ventured beyond low Earth orbit in their lifetime. The International Space Station, for all its genuine scientific value, and its remarkable continuous human habitation since the year 2000, orbits at approximately 250 miles above Earth's surface. That is high enough to see the curvature of the planet. It is not high enough to leave the neighbourhood. Artemis II is going to leave the neighbourhood. The mission, NASA's first crewed lunar flight under the Artemis program, will carry 4 astronauts into cislunar space, the region of space between Earth and the Moon that no human being has occupied since the crew of Apollo 17 returned in December of 1972. The trajectory will take the crew approximately 230,000 miles from Earth, looping around the Moon in a free return trajectory before bringing them back to a splashdown in the Pacific. They will not land on the lunar surface. The landing is reserved for a later mission. But they will spend approximately 10 days in an environment so fundamentally different from anything experienced by astronauts on the International Space Station that the comparison almost fails to communicate the difference. To understand why, you need to understand something about the invisible architecture that makes life on and near Earth possible. Earth is wrapped in a magnetic field generated by the movement of molten iron in the planet's outer core. This field, the magnetosphere, extends tens of thousands of miles into space in all directions, forming an asymmetric bubble that is compressed on the sun-facing side by the pressure of the solar wind and stretched into a long tail on the opposite side. Within this bubble, charged particles from the sun and from deep space are deflected, trapped, or slowed before they can reach the surface. The magnetosphere is not a perfect shield. Some radiation penetrates. Astronauts aboard the International Space Station receive radiation doses meaningfully higher than people on the ground, and long-duration ISS missions carry associated health considerations that NASA manages carefully. But the ISS crew is operating within the magnetosphere, inside the bubble, with the full deflecting power of Earth's magnetic field between them and the unfiltered solar environment. The crew of Artemis II will leave that bubble. Once their spacecraft travels beyond the magnetosphere, somewhere between 10,000 and 40,000 miles from Earth, depending on the direction of travel relative to the Sun, they will enter the interplanetary medium, the raw solar environment, the space that exists between planets, swept by the solar wind at all times, and occasionally punctuated by the arrival of solar flares and coronal mass ejections that carry radiation doses orders of magnitude above the background level. There is no magnetosphere in interplanetary space. There is no atmosphere. There is nothing between the crew and the Sun except the walls of their spacecraft and whatever shielding has been engineered into the vehicle's design. This radiation environment is one of the central unsolved challenges of human deep space exploration. We know, with reasonable precision, what the background radiation dose in interplanetary space looks like during quiet solar conditions. We know it is manageable for a mission of approximately 10 days duration, which is why Artemis II can proceed safely. What we know with less precision is the dose associated with an acute solar particle event, a major solar flare or coronal mass ejection arriving during the mission window, and specifically whether the spacecraft's shielding and the crew's shelter protocols would be adequate to protect them from the worst-case events that a still-active solar cycle 25 could produce. NASA has procedures for this. The spacecraft has a designated shelter area with higher shielding mass. Space weather forecasters will be monitoring the sun continuously throughout the mission and providing real-time warnings. But the warning time for a fast CME is measured in hours, not days, and the uncertainty in both the timing and the intensity of solar particle events remains a genuine operational challenge. This is why Artemis II is not just an exploration mission. It is a living scientific experiment in human exposure to the deep space radiation environment, conducted with instruments, protocols, and monitoring systems that did not exist during the Apollo era. The mission will carry dosimetry equipment capable of measuring radiation exposure in real time, both for the crew members individually and for the spacecraft environment as a whole. Passive dosimeters will record cumulative dose. Active detectors will measure the timing and energy spectrum of radiation events as they occur. Phantom torso experiments, essentially instrumented mannequins placed in various locations within the spacecraft, will map the radiation field throughout the vehicle and identify which positions and postures provide the greatest protection during solar particle events. All of that data, collected over 10 days in the actual interplanetary radiation environment during an active phase of the solar cycle, will be more valuable to the design of future deep space missions than decades of ground-based modelling. The feedback loop between crewed deep space missions and space weather prediction capability is direct and consequential. Better understanding of how solar particle events propagate through the interplanetary medium, how their intensity varies with distance from the Sun, and how spacecraft structures interact with different types of radiation, requires measurements taken in the actual environment. Ground-based models can simulate these interactions, but they are only as good as their input data, and the input data for interplanetary radiation environments is sparse compared to the data available for near-Earth conditions. Every measurement taken by Artemis II improves the models. Better models mean better predictions. Better predictions mean more warning time. And more warning time for both astronauts in deep space and infrastructure operators on Earth's surface is the single most valuable commodity in space weather response. Consider what an additional 2 hours of warning time would mean for a grid operator facing a major geomagnetic storm. 2 hours is enough time to reduce the loading on vulnerable high-voltage transmission lines, to bring large transformers to a safer operating state, to coordinate with neighbouring grid regions on protective switching. The difference between a major geomagnetic storm that causes manageable disruption and one that causes transformer failures requiring months of repair time is often a matter of preparation, and preparation is a function of warning time. The science that improves warning time for astronauts in cislunar space is the same science that improves warning time for the power systems serving hospitals, water treatment facilities, and the millions of air conditioning units currently running at maximum capacity under a record-breaking heat dome in the American Southwest. There is a larger and more speculative connection worth acknowledging here, not as established science but as an active area of legitimate research. The question of whether solar variability influences Earth's atmospheric circulation patterns beyond the direct effect of changes in solar irradiance remains genuinely open. The total energy output of the Sun varies by only about 0.1% between solar minimum and solar maximum, a variation too small to directly drive the kinds of atmospheric changes we have been describing. But there are proposed mechanisms involving the Sun's ultraviolet output, which varies more significantly than total irradiance, and its potential effects on stratospheric ozone chemistry and temperature gradients that could in theory influence the jet stream behaviour we discussed earlier in this video. There are also proposed mechanisms involving galactic cosmic ray flux, which varies inversely with solar activity and has been hypothesized to influence cloud formation and atmospheric electrical properties. None of these mechanisms has achieved scientific consensus. All of them are being studied with serious instruments by serious researchers. The relationship between solar activity and Earth's climate system, at the level of atmospheric dynamics rather than just surface temperature, is one of the more genuinely uncertain and important questions in Earth system science. The data that Artemis II and subsequent deep space missions will generate cannot answer that question directly, but it will improve our understanding of the near-Earth solar environment in ways that feed into every model that touches the interface between space weather and Earth's upper atmosphere. Science does not usually deliver answers in straight lines. It delivers measurements that improve models that generate hypotheses that demand better measurements. Artemis 2 is the next measurement, and it is being taken at a moment when the questions it will help answer have rarely felt more urgent. In a week when the Sun is active, the atmosphere is behaving beyond its historical parameters, and the distance between what we know and what we need to know has rarely felt more consequential. While 4 human beings prepare to venture further from Earth than any person has travelled in half a century, the orbital infrastructure that watches our planet from much closer distances is itself undergoing an expansion of its own, one that has already crossed a threshold that would have seemed implausible even 10 years ago, and that carries both extraordinary promise and a set of complications that nobody has fully resolved. Part 14. 10,000 satellites and a changing sky. SpaceX reached a milestone this year that would have been dismissed as science fiction a decade ago. The Starlink satellite constellation crossed 10,000 operational satellites in orbit, 10,000 individual spacecraft, each one launched, deployed, and maintained by a single private company, collectively forming the largest constellation of active satellites in the history of human spaceflight by an enormous margin. To put that number in perspective, the entire history of human space activity, from Sputnik's launch in 1957 through every government space program and commercial satellite operator across 6 decades of the space age, produced fewer than 10,000 objects sent to orbit in total before SpaceX began its Starlink deployment in earnest. The company has now matched that cumulative historical total with a single product line, and the constellation continues to grow. New batches of satellites launch on a cadence that, a decade ago, would have described an ambitious annual launch program for an entire national space agency. SpaceX is doing it every few weeks. The stated purpose of the Starlink network is global broadband internet coverage, with particular emphasis on reaching communities and regions that lack reliable terrestrial internet infrastructure. The realized benefits in that domain are real, documented, and in many cases genuinely life-changing, in ways that deserve acknowledgement before we get to the complications. Remote communities in rural Alaska that previously had no viable high-speed internet connection now have access to telemedicine consultations that can substitute for the medical evacuations that used to be their only option for specialist care. Agricultural operations across the Central African Plateau that had no connectivity now have access to real-time weather data, market pricing information, and precision farming guidance. Maritime vessels crossing the Southern Ocean, research stations in Antarctica, emergency response teams operating in disaster zones where terrestrial infrastructure has been destroyed, all of these users now have access to a communications capability that simply did not exist for them before Starlink. These are not marginal improvements. They are transformative changes in the information environment available to some of the most isolated people and operations on Earth, and they are worth holding alongside the more complicated parts of this story. But the Starlink network and the mega-constellation era it has inaugurated represent something considerably more layered than a connectivity infrastructure story. They represent a new and largely unplanned layer of observational capability that is only beginning to be understood and utilized for purposes beyond the commercial design intent of the satellites themselves. The density and global distribution of a 10,000 satellite constellation means that at any given moment, hundreds of those satellites are passing over every region of Earth's surface, including the remote ocean areas and polar regions that have historically been the most data-sparse zones in global atmospheric monitoring networks. The sensors aboard those satellites, the thermal infrared detectors, the communication link performance monitoring systems, the precision accelerometers used for orbital drag measurement. All of these instruments are continuously generating data streams that contain embedded information about the atmospheric and ionospheric environment through which the satellites are moving. Researchers at several universities and government laboratories have begun mining those data streams for scientific content that was never the primary purpose of the instruments generating it. Atmospheric drag measurements, for example, which SpaceX collects continuously to manage orbital maintenance of the constellation, encode information about upper atmospheric density that varies with temperature, solar activity, and large-scale circulation patterns. When an extreme heat event drives unusual warming in the upper atmosphere, that warming changes the density profile of the atmosphere at satellite altitudes in ways that show up in the drag data. When a geomagnetic storm perturbs the ionosphere, that perturbation affects the propagation characteristics of the communication signals passing through it in ways that the link performance monitoring systems record. The constellation is, inadvertently and continuously, taking the atmosphere's temperature from above across the entire globe at a spatial and temporal resolution that no purpose-built observing network has ever matched. The question this raises, the one that connects directly to everything we have been discussing throughout this video, is both simple to ask and genuinely difficult to answer. Can more data fix the prediction gaps we have been describing? If the underforecasting problem that opened this story, the pattern of weather models consistently underestimating observed temperatures during this heat event, is partly a function of insufficient input data, specifically insufficient high-resolution real-time data about upper-level atmospheric conditions over remote regions and data-sparse areas, then satellite constellations that continuously sample those regions might, over time, contribute meaningfully to improved model performance. The atmospheric models that generate weather forecasts are only as good as the observations that initialize them. Garbage in, garbage out, as the saying goes, but the inverse also applies: better observations in, better forecasts out. In principle, the data density that a 10,000 satellite constellation can provide should help. The honest qualification is that the principle is sound, but the magnitude of improvement is genuinely uncertain. Weather forecast model performance is not limited solely by data quantity. It is also limited by model resolution, by the parameterization of physical processes that occur at scales too small to resolve explicitly, by computational constraints on how frequently models can be updated and at what spatial resolution, and by fundamental limits on atmospheric predictability imposed by the chaotic nature of fluid dynamics. More data helps with the initialization problem. It does not help with the chaos problem. The atmosphere becomes fundamentally unpredictable beyond certain time horizons, regardless of how good the initial conditions are, and no amount of satellite data changes that mathematical reality. But within the ranges where predictability is theoretically achievable, better observations should translate to better forecasts. The question of how much better and how quickly that improvement materializes in operational forecast systems is one that the meteorological community is actively working to answer. The downside of the mega constellation era is also real, and it is being taken seriously enough by the scientific community that it deserves equal time in any honest account of what 10,000 Starlink satellites actually means for our relationship with the sky. The brightness of Starlink satellites as seen from Earth's surface has been documented extensively by ground-based observatories, and the documentation is not encouraging. Long-exposure telescope images taken during the early deployment phase of the constellation showed linear streaks crossing the field of view, each streak representing a single satellite passing through the frame during the exposure. Those streaks cannot always be removed in post-processing without discarding the data beneath them, which means that for some observations, the satellite passage simply destroys the scientific value of the image. Astronomers studying faint transient events, the brief optical signatures of gravitational wave sources, gamma-ray bursts, near-Earth asteroid detections, have found their work increasingly complicated by a sky that is no longer dark in the way it was when their observatories were designed and their techniques were developed. SpaceX has made genuine engineering efforts to reduce the brightness of Starlink satellites, implementing sunshade visors and modified orbital orientations that reduce reflected sunlight during the most sensitive observing periods. These efforts have produced measurable improvement. They have not solved the problem, and as the constellation grows toward the tens of thousands of satellites that SpaceX has permission to deploy, the improvement achieved per satellite is overwhelmed by the increase in total satellite count. The night sky, observable from Earth's surface, is a finite, irreplaceable scientific resource that has been accumulating observational value for as long as human beings have been building telescopes. Its degradation, even incremental and partial, is permanent in a way that most infrastructure trade-offs are not. A road can be rerouted. A building can be demolished. Photons that were never collected because a satellite passed through the field of view of a telescope at the wrong moment are gone. That data does not exist. The observation was not made, and some fraction of what that observation might have revealed, a new near-Earth object, an early warning of a solar event, a previously unknown variable star, remains unknown. There is also the orbital debris dimension, which operates on timescales longer than most infrastructure planning horizons, but with consequences that could affect every future use of certain orbital altitudes for generations. 10,000 operational satellites generate a debris environment that includes failed satellites awaiting deorbit, spent rocket upper stages, and the growing population of collision fragments produced when objects in crowded orbits occasionally strike each other. The probability of a Kessler syndrome event, the cascading chain reaction of collisions first described by NASA scientist Donald Kessler in 1978, in which each collision generates debris that causes further collisions in a self-sustaining cascade that renders certain orbital altitudes permanently unusable, increases non-linearly with the density of objects in those altitudes. The responsible governance of orbital space as a shared resource, a commons belonging to all of humanity and to future generations, is not keeping pace with the rate at which it is being populated. This is not a problem with a simple villain. It is a tragedy of the commons problem, the kind where individually rational decisions by multiple actors produce collectively irrational outcomes, and it is playing out in real time above our heads. But for the immediate and urgent question of whether humanity can see extreme atmospheric events coming more clearly, with more lead time, and with enough accuracy to protect the people and infrastructure in their path, the answer that the mega-constellation era is slowly developing is possibly yes, and possibly significantly so. More data, better processed, fed into models that are themselves improving, might meaningfully narrow the gap between forecast and reality that opened this story. The question that remains, and that connects to every part of this week's convergence of anomalies, is whether that improvement arrives fast enough to be useful for the kinds of events that are now occurring. Because the atmosphere is not waiting for the models to catch up, and what comes next, in the weeks and months and seasons ahead, may be the most important question the data has asked us yet. Part 15. If this is March, what is summer? We need to talk about what happens next. Not next week, though next week matters and we will get there. Not next month, though next month carries its own weight in this story. What we need to talk about is the larger context, the seasonal and climatic architecture within which the event we have been describing all week is embedded. Because the heat dome sitting over the United States right now did not arrive randomly. It did not fall out of a clear sky without precedent or context. It arrived during a specific phase of the most powerful year-to-year climate variability pattern on Earth, and that phase has implications for everything that follows, through the spring, through the summer, and into the fall of 2026. Understanding that context does not make the current event less alarming, it makes it considerably more so. The El Niño Southern Oscillation, known by its acronym ENSO, is the dominant engine of year-to-year climate variability across the entire planet. It is not a regional phenomenon, it is a global one. At its core, ENSO describes the periodic warming and cooling of sea surface temperatures across the central and eastern tropical Pacific Ocean, a body of water so large that its thermal state influences atmospheric circulation patterns on every inhabited continent. When sea surface temperatures in that region are warmer than average, the atmosphere above them responds by reorganizing its circulation in ways that have predictable, if probabilistic, downstream effects. That warm phase is called El Niño. When sea surface temperatures in the same region are cooler than average, the circulation reorganizes in the opposite direction. That cool phase is called La Niña. Between those two poles, the system moves through neutral conditions, neither strongly warm nor strongly cool, during transition periods that can last months. For the past several years, the dominant ENSO state has been La Niña, a cool phase that has influenced precipitation patterns, drought conditions, and temperature distributions across North America and beyond. La Niña tends to drive below-average precipitation across the southern tier of the United States and warmer-than-average conditions across parts of the northern tier. It has contributed to the drought conditions that have been building across parts of the Southwest and Great Plains for an extended period, drying out the very soils and vegetation that are now functioning as critical fire fuel under the current heat event. La Niña has been part of the background story all along, even when it was not being mentioned by name. That La Niña pattern has now weakened. The tropical Pacific is transitioning toward neutral ENSO conditions, and climate models are beginning to suggest the possibility of El Niño development through the remainder of 2026. The transition is underway, but it is not complete. The warm El Niño signature has not yet materialized in the sea surface temperature data with enough strength or persistence to be formally declared. What we have right now is a system moving between states, no longer strongly La Niña, not yet El Niño, occupying the relatively quiet middle ground that climatologists call ENSO neutral. Here is the sentence in this entire story that deserves the most careful reading. The extreme heat event we have been describing, the 99th percentile atmospheric heights, the all-time March temperature records, the fire weather conditions drier than the Sahara across tens of millions of acres of the Great Plains, is happening in ENSO neutral conditions. The heat amplifier is not on. The large-scale oceanic warming pattern that typically adds a systematic boost to summer and autumn temperatures across the American South and West has not yet engaged. What we are watching right now is the atmosphere producing a record-shattering March heat event, using only the tools available to it in a background state that is, by ENSO standards, relatively unremarkable. It is doing this without the El Niño boost. It is doing this before the summer sun angle has maximized solar input. It is doing this before the land surface has had time to accumulate the additional dryness that normally builds through June and July. It is doing this, in other words, with one hand tied behind its back. If El Niño develops through the summer and fall of 2026, as some models are beginning to suggest is possible, it would add a systematic, large-scale warming influence on top of whatever the seasonal cycle produces independently. El Niño summers over the American West and South are not just warmer than average. They are warmer in a sustained, large-scale way that interacts with local weather patterns to produce heat events with greater frequency, greater intensity and greater duration. The drought conditions that El Niño tends to amplify across the southern tier would further dry the fire fuels that are already at critical moisture levels. The heat that El Niño tends to add to the warm season would be arriving on top of a background atmospheric state that has already demonstrated its capacity to produce 99th percentile ridging in March, before any seasonal amplification has occurred. The National Weather Service has also indicated that the specific atmospheric pattern driving the current heat event is not expected to fully break down before some form of elevated heat returns to the region. There will be a transitional period. There will be some moderation. But the large-scale atmospheric configuration that enabled this event, the tendency toward amplified ridging over the western United States, the weakened jet stream behavior that allows blocking patterns to persist, is not going away between now and summer. This event is not an isolated exclamation point in an otherwise normal year. It is a data point in what is beginning to look like a sentence, possibly a paragraph. The pattern has persistence, and persistence in atmospheric science, as we discussed earlier in this video, is more consequential than intensity. The seasonal boundaries are shifting. This is not a political statement. It is not an advocacy position. It is a description of what the observational record is showing across multiple independent data sets. March used to be reliably transitional in the American West and Great Plains. Temperatures in March used to climb gradually from winter levels towards spring levels, staying reliably below the thresholds that trigger red flag fire weather warnings, staying reliably below the thresholds that challenge all-time temperature records, staying reliably within the range that the forecast models built on historical data were designed to represent. The month of March, in the statistical climatology that underlies every forecast model and every emergency preparedness framework in the country, was a safe month, a mild month, a month that did not require the same level of fire weather vigilance as July or the same infrastructure stress planning as August. If the first day of astronomical spring can now deliver June temperatures to Denver, can generate fire weather conditions severe enough to trigger multi-state emergency alerts across tens of millions of acres, can produce upper-level atmospheric heights at the 99th percentile of the historical record, and can consistently outrun the forecast models built on decades of observational data, then the assumptions embedded in our seasonal calendars may need systematic revision. Not just the weather forecasts. The seasonal calendars that organise our agricultural systems, our wildfire preparedness cycles, our infrastructure maintenance schedules, our public health heat emergency protocols. All of these systems were designed around a version of the annual cycle that included certain expectations about when extreme conditions could occur. Those expectations were not arbitrary, they were based on data. But the data they were based on described a climate that may be receding in the rearview mirror faster than the systems built on it can adapt. Consider what this means in practical operational terms. Wildfire preparedness in much of the American West is organised around a fire season that traditionally begins in late spring and peaks in late summer and early fall. The staffing levels at fire suppression agencies, the pre-positioning of aerial firefighting assets, the activation of emergency coordination centres, all of these are calibrated to a seasonal timeline. If significant fire weather conditions are now possible in March, before the traditional fire season has even begun, before the full complement of preparedness resources has been deployed, before the public has shifted its awareness from winter to fire season mode, then the margin between a manageable fire event and a catastrophic one narrows, not because the firefighting capability has decreased, but because it has not yet fully assembled when the conditions arrive. This is the thought to carry forward from everything we have discussed tonight. The atmosphere is not reading from the same script it used to read from. The models trained on historical behaviour are being outpaced by present behaviour at the exact moments when accurate prediction matters most. The extremes that once occupied the statistical tails of the distribution, the 99th percentile events that by definition should occur no more than 1% of the time, are appearing with a frequency and intensity that is beginning to challenge the statistical frameworks we built to understand and manage them. If this is what March looks like in 2026, before El Niño, before the summer sun angle, before the peak fire season, before the accumulated dryness of a full summer, then the months ahead carry a weight that the calendar does not yet reflect. Summer is coming, the heat amplifier may be turning on. The blocking patterns that enabled this event are not structurally resolved, and the forecast models that should be our early warning system are running systematically behind reality at precisely the moments when reality is most consequential. The most alarming thing about a 99th percentile event is not the event itself. Events happen, records fall, extremes occur. The alarming thing is the possibility, growing more difficult to dismiss with each successive season of data, that what we are calling the 99th percentile today is not a permanent category, that the distribution is shifting, that the tail is becoming the body, that by the time the next decade's data has been collected and the statistics have been recalculated, what we are breathlessly documenting tonight as an extraordinary anomaly will have a new name, not a record, not an extreme, just a warm March, just another Tuesday.